to talk about the uranium ditelluride. I mean, the reason I sort of invited him to give this talk was because he had this very nice review article summarizing all the systematics in the uranium system, basically categorizing the key features of spin-triplet superconductivity and the whole phase diagram. So yeah, so hopefully, I mean, by given 1 hour, we should have enough discussion. Also, there are some issues concerning, whether the uranium ditelluride has 1 or 2 transitions. This was sort of inspired by previous, discussion with Daniel. So I hope this will at least clarify some of the situation from, experimental point of view. Yeah, here you go, Dr. Aoki. Yeah, so the floor is yours. Yeah, thank you.
Yeah. Thank you, Penchen. So first of all, I'd like to thank for this opportunity. So today I'm going to talk about uranium ditelluride, so focusing on the multiple superconducting phases and the field-induced phenomena. So my collaborators is following. So of course we are collaborating very closely with CA people or the other colleague in France. So Georg Knebel, Daniel, Alex, and Jean-Pascal, and Cugnu, and Bariska, and Gerard Lapelto, and Jacques Fulke. And here is my colleague in Tohoku University. And also we collaborate with Atsushi Miyake in ISSP and LCME in France, William and Ilya, and Kobe University, Harima. And so here is also, I want to acknowledge many people, so our colleague, so especially for NMR study by Ishida-san and Tokunaga-san. And also, yeah, so here is the list of my colleagues. And the review paper of ferromagnetic superconductivity, as Penchen said, so it's already published here, so you can look, so if you have interest. And so very recently, in fact, last week, so we submitted the new review paper on radium ditelluride with Jean-Pascal, Jacques, and Kenji, and Georg, and Yo, and Yanase-san. So we will submit in the archive also. So please look at if you have interest. So the contents of my talk is following. So here is I introduce about the radium ditelluride and also compare with the ferromagnetic superconductor and basic properties I present. And one of the highlights of radium ditelluride is field-reentrant superconductivity. I want to explain this. And then, so I will show you our result of multiple superconducting phases under pressure. And so I also want to emphasize that superconductivity is induced in field-induced superconductivity observed just above PC, critical pressure. And I want to show you the magnetic property, how the anisotropy change under pressure. And then I summarize my talk. So as an introduction, I want to show you the list of uranium-based heavy fermion superconductor. So here you can see many heavy interesting materials. The first discovery was done first discovery was uranium barium-13. It's a long time ago, 1983. But so so there are many, and the light blue color means the candidate of the spin-triplet superconductivity. So you can understand. So so there are many candidates for spin-triplet superconductivity. So here is this is radium germanium-2, the ferromagnetic superconductor, and rhodium and cobalt, and the uranium ditelluride is here. So so this is a schematic view to show the relation between magnetism and superconductivity. So so magnetism and superconductivity was antagonistic each other. But after the discovery of selenium kappa 2 silicon 2, so new region appears. This is so-called unconventional superconductivity. And nowadays there are another axis so-called topological science or topological materials. And so the uranium ditelluride or uranium ferromagnetic superconductor is exactly located here. So this region is a topology we can call topological spin-triplet superconductivity. So the uranium ditelluride is quite important materials to search for this region. So I want to say that topological materials meet the strongly correlated electron systems. So another view, this is a view of Yanase-san. So he showed that so S-wave superconductivity is quite usual, and there are many materials, but to tune the topological superconductivity is quite difficult. So we need to manipulate somehow. And so this is quite rare. Topological superconductivity is rare. On the other hand, spin-triplet superconductivity, the material is quite rare. However, the topologically it is as it is. So and uranium ditelluride is located here. So it is in important materials. So this materials is first discovered by Shen Ran, Nick Butch, and Jean Paglione's group. So and this is the first. So I took this figure from the first paper in 2019 of Science. So they show the schematic view of to show the relation between uranium ditelluride and ferromagnetic superconductor. The horizontal axis is the ordered moment or the spin fluctuation. So uranium germanium 2, the ordered moment is about 1 μb, and uranium rhodium germanium 0.4 μb, and uranium cobalt germanium, this is weak ferromagnet, 0.05 μb. So then, the vertical axis is the temperature for the ferromagnetic order or the superconductivity. So uranium ditelluride is located here because this is paramagnet. It's not ferromagnet, but it is believed to at the verge of ferromagnetic order. But I would emphasize that this is a very good starting point, but maybe it is too simplified. So here, I want to show you some highlight of ferromagnetic superconductivity and uranium ditelluride. So uranium, rhodium, germanium, and cobalt germanium, as I said, the ordered moment is 0.4 or 0.05 μb. And when we apply the magnetic field along hard magnetization axis, B axis, so Curie temperature is suppressing with field, and then the superconductivity is enhanced. Here it shows the reentrant superconductivity, and the TC at 12 Tesla is about 0.4 μb, but at zero field, the TC is only 0.25 Tesla, 25 Kelvin. So the superconductivity is really enhanced under magnetic field. And similarly, so uranium, cobalt, germanium, HC2 curve is very peculiar. So it shows a vertical increase here. And this vertical increase is connecting to the suppression of T Curie. On the other hand, uranium ditelluride, so this is also very interesting. So TC is 1.5 or 1.6 Kelvin, and superconductivity is suppressed, but so that it shows a reentrant superconducting behavior up to 35 Tesla. So the HC2 is quite high, and this enhancement is connecting to the metamagnetic transition, first order metamagnetic transition, HM. So and then above HM, the superconductivity is immediately suppressed. Sorry, and this HM is connecting to the so-called T chi max. This is not transition. It's a kind of crossover. detected by the susceptibility, and then so it's changing to the first order transition through the critical endpoint, and then so changing to the HM. And this is a case for the radium telluride. So, and so another view is angular dependence of HC2. So uranium, rhodium, germanium, and cobalt germanium. So you can see the reentrant superconducting region appears when the field is applied along hard magnetization axis here or here. This kind of acute enhancement of HC2 cannot be explained by the usual effective mass model, of course. So we can understand that probably the very anisotropic Ising type ferromagnetic fluctuation is important to induce superconductivity for these materials. And in radium ditelluride, it also shows quite an isotropic HC2. So you can see, so when the magnetic field applying along B axis, so we observe the reentrant superconductivity. By the way, the data is taken from the paper by Wang. So, and here this is the H metamagnetic transition. And one of the interests is there is another superconducting pocket above the HM when the field is applied around 30 or around 30 degrees, tilting from B to C axis. So this is the kind of highlight. Now I want to show you the basic properties of radium ditelluride. So this material is paramagnet, heavy fermion paramagnet. The gamma value is 120 millijoule, and the crystal structure is body centered. So this is the crystal structure, and the C axis is longer than the AB axis, and so here it shows the distance between first nearest neighbor, second nearest neighbor, and third nearest neighbor. So the first nearest neighbor is larger than the Hill limit. So we can naively consider that the magnetic order, but in fact it is not. And the crystal structure consists of two-leg ladder structure, and theoretically magnetic frustration is proposed by the early paper by Xu and et al. So they calculate the antiferromagnetic interaction and ferromagnetic interaction, and they discuss for the interaction, both interaction. And from the band calculation, the bare LDA band calculation shows the Kondo semiconducting behavior. So this is the band structure, and here is the Fermi energy. So you can see the small gap appears at the Fermi energy around 130 Kelvin, and the band is rather flat. So this is something like a Kondo semiconducting behavior. So, but in the reality, the uranium ditelluride is a good metal. So this is not the real case. And Ishizuka-san and Yanase-san, so they calculate, so with GGA plus U calculation. And then so by changing the U, the Fermi surfaces appears something like this. And the volume of Fermi surfaces, depending on the number of the Coulomb repulsion U. And I believe the reality, it is something like this. And the magnetic properties, so I want to show you, here is a magnetic susceptibility for A, B, C axis. So this is a paramagnet, so there is no magnetic order, but so there is a large anisotropy between A, B, C axis. So for B axis, so you can see the so-called T chi max, broad maximum. This is about 35 Kelvin. And if you look at A axis, so we can see the broad shoulder. So we call T star appearing at 15 Kelvin. And so this the broad maximum 35 Kelvin is connecting to the metamagnetic transition. This is a magnetization curve at low temperature. So you can see the ABC axis is quite anisotropic. But when we apply the magnetic field along B axis up to 35 Tesla, so we can see the sharp metamagnetic transition here. So this, this is the first order metamagnetic transition. And this first order metamagnetic transition is connecting to the T chi max here. And here is the critical endpoint changing to the first order transition. So the resistivity curve is following for A and C axis, so that you can see the typical behavior of heavy fermion system. And when we apply the current along C axis, we can see the T star, so-called T star. This is not the kink, but the sharp anomaly appearing around 15 Kelvin. And at low temperature, so we can see this superconducting transition at 1.6 or 1.7 Kelvin. And here is a specific heat curve. So this is also very sharp. And so the interesting point is large residual density of the state at low temperature. So I will show you more details. And so, of course, to study these materials, the high quality single crystal is quite important. So we are growing the many single crystals using the chemical vapor transport method. This is the crystals. And to get these materials, so we use this kind of quartz ampoule, and it takes about two weeks or 10 days. And nowadays, so we have 0.5 gram or about up to 1 gram of single crystal is obtained. And so we also checked by single crystal X-ray analysis, and the crystal structure is okay, and the composition is 1 and 2. Now, so we so batch number is more than 70. So we are so stupidly, so we are repeating and to try to get higher quality single crystals. And for concerning the specific heat jump, so there is a debate. So either if it is a single transition or double transition. So after repeating the crystal growth, so we also get the crystal with double transition. So here is I pick up several materials, single crystals, and in our experience for the sample which shows the double transition is lower quality, and the single transition shows a higher quality. So here is a kind of example. And this is the relation between TC and residual density of state, gamma. And so you can see if the quality is better, so the residual density of states is getting smaller and smaller. And so in our sample is about less than 40% of residual density of state is obtained. And quite recently, the Los Alamos group shows the TC about 2 Kelvin. In this case, so the data point is nearly the extrapolations for this curve, and it's around here, I think. And so concerning the residual density of states, I want to remind you the case for ferromagnetic superconductor. This is so uranium germanium 2, rhodium germanium, and cobalt germanium. Of course, to measure the specific heat, so we need to measure the best quality sample. So here we measure the sample with RRR 600, 120, or 165. So they are very good single crystals. And these are ordered moment 1 μb, 0.4, and 0.05 μb. So you can understand that even so high quality single crystals, so it shows a large residual density of state, and this may relate it to the ordered moment. So if you plot so the residual density of state and ordered moment, so it follows something like this. And so if the ordered moment is 0, so the residual density of state is basically 0. And this is also theoretically explained by Kusunose-san and Kimoto-san. So this is the residual density of state and ordered moment. So it is something like this. And this residual density of state in ferromagnetic superconductivity was explained by the scenario of self-induced vortex state. So it means even in the zero field, so superconducting mixed state is realized. And experimentally, the magnetization or NMR support this scenario. So coming back to the rhenium ditelluride, I want to show you briefly the night shift experiment by Kenji Shida's group. So this is a night shift as a function of temperature. So below Tc, so night shift is slightly decreasing, but it's only 0.1%. This is very small. So the compared to the total spin susceptibility, so this is a spin susceptibility. So you can see the decrease of night shift is very small. So this is much smaller than the expected case for the spin singlet. So we can believe, so this is a kind of evidence for the spin triplet state. So the for the HT phase diagram, so the one of the highlight is the spin reentrant superconductivity, as I said. So this is a magnetic resistance as a function of field. So you can see the reentrant behavior. For example, if you look at 0.6 Kelvin, so it shows the suppression of superconductivity is killed, but it reappears. And then the superconductivity is finally suppressed at 35 Tesla. And this is a HC2 curve for ABC axis. So AC axis is about 7 Tesla or 11 Tesla, but B axis is 35 Tesla. So HC2 is 35 Tesla, and here is HM. So for all field direction, the HC2 is larger than the power limit. Power limit is only 3 Tesla assumed within the weak coupling BCS theory. So we can naively think about the possibility of spin triplet state. And from this phase diagram, the HC2 phase diagram, so there are several theoretical scenarios by Machida-san, Yanase-san, and Shishido, and Daniel. And so now I want to also emphasize the reentrant superconductivity when the field is applied along tilted field direction from B to C axis. This is the angular dependence taken by Chen-Lan's paper. So we confirm the reentrant field-induced reentrant superconductivity at 30 degrees. So this region. So this is the paper by William Knafo. And so recently, so we measured the magnetization for ABC axis and 011 direction, which means about the field direction is about 30 degrees. So you can see even in the 011 direction, so we can see the clear metamagnetic transition. And HM is basically follows the 1 over cosine theta behavior. And the important point is when we apply, when the field is tilted to the 30 degrees, so the gamma value, the jump of gamma value changing. So here is temperature field dependence of the phase diagram, and here is the gamma value as a function of field taken analyzed through the Maxwell relation and Clausius-Clapeyron Clausius-Clapeyron equation, because this metamagnetic transition is the first order transition. So we can precisely, so we can estimate how much is the jump of the gamma value through this Clausius-Clapeyron relation. So we know the delta m, and also we know the second derivative of hm. So then, we can get the Clausius-Clapeyron, the delta gamma. So when the field is applying along b-axis, the gamma value is drop, so at hm. On the other hand, when the field is applied along 30 degree, so the gamma value is jumped positively. So this enhancement is maybe important to show the reentrant superconductivity. And this different behavior may be due to the two interactions, namely the ferromagnetic interaction and antiferromagnetic interaction plays an important role. And this is the field direction is tuning for these two correlations. Now I want to show you the multiple superconducting phases in radium ditelluride. So here is the temperature pressure phase diagram at field at H equals 0. So applying the pressure, the superconductor TC is suppressing, but at 0.25 0.2 GPa, so TC is suppressed, is split. So one is increase and the other is continuously decreasing, something like this. And clearly, so there are two superconducting phases appears. So this is detected by the thermodynamic signal by AC calorimetry measurement. So this is the example. So 0.5 GPa. So you can see the double transition, and further increasing the pressure. So you can see the double transition, the evolution of the double transition. And finally, so the superconductivity is suppressed at 1.5 GPa, and magnetic order appears. So we call magnetic order MO and WMO. So we think magnetic order is most likely antiferromagnetic order, and weak magnetic order is probably due to the short development of short range order, but we don't know yet. So this multiple superconducting phases is similar to the well-known cases of UTe3 or thorium-doped uranium-barium-13. So the multiple superconducting phases is observed in UTe3, and the order parameter are different between different phases, and uranium-barium-13 as well. And of course, so well-known cases is with helium-3. So A and B phases are known, something like this. And this is a kind of evidence for the evidence for spin-triplet state, because spin-triplet state, so there is a spin and orbital degree of freedom. So there is a possibility for this kind of multiple superconducting phases. So applying the pressure, so the lattice parameter also drastically changing. So this is pressure dependence of A, B, C axis and the volume. So you can see the quite large changing of lattice parameter. And so if you take the volume, so at 1.5 GPa, so delta V over V is about reaches about 3% reduction. This is very large. And this drastic change induce the magnetic property, induce the new magnetic order state or valence instability. And also, I want to emphasize that the paper by Futanu at low temperature, the distance between the first nearest neighbor is reduced. So they report so up to the 60% reduction between this random distance. So this is very large. This may indicate the changing of the magnetic interaction. So here I want to show you the phase diagram. So when the field is applying along a-axis and under pressure, so we observe by magnetic resistance, so very peculiar AC2 curve. So the AC2 is increasing at low and high field region. And this enhancement reminds us the case for FFLO state, but I would say no. So because FFLO state, so the increase is typically very small, something like this. But in this case, so more than 30% increase detected. So then, we started to measure AC calorimetry again under pressure and under magnetic field. So first we detected, we also confirmed the double transition and also the field scan of AC calorimetry. There are several anomalies. So from this anomaly, so we can construct the phase diagram. This is the HT phase diagram at 0.5 GPa. So it is here. So in fact, so this HC2 enhancement is connecting to the lower TC. Lower TC is vertically increasing with field. Then so the connecting to the enhancement of HC2. So it indicates that multiple superconductivity also appears under magnetic field. These multiple superconducting phases are also theoretically explained by Machida-san, Shishido-san, and Ishizuka-san, so on. And this is a summary for A-axis. It indicates the evolution of multiple superconducting phases. So first it is a single phase, but so multiple superconductivity appears something like this. And then, so finally, so SC4 and SC3 is decoupled, and then the magnetic order appears, something like this. Okay, so for B-axis, so the reentrant superconductivity appears, is known at ambient pressure, and under pressure, so the phase diagram changing following. So the HM metamagnetic transition suppressing with pressure, and then so the reentrant superconductivity is also suppressed, something like this. And the pressure dependence of HM is shown here, something like this. And this is basically consistent with the evolution of T chi max. I will show you later. And another point is at metamagnetic transition, there is a large volume change is known. So from the evolution of DM pressure dependence of HM or BM, so we can predict the volume change. So from this Clausius-Clapeyron relation, so we can estimate the delta V over V at HM is 0.1% reduction at P equals 0. And indeed, so if we measure, well, this is a case under magnetic field, under pressure, because the magnetic field is too high for us, but we measure the magnetostriction, and so you can see the reduction of the magnetostriction, and clearly there is a hysteresis. Of course, to get the volume, so we need to measure B and C and A axis, but this is a good indication. And for C axis, so here you can see the evolution of HC2 curve, and so with increasing pressure, so the slope of HC2 increases rapidly, and 1.34 GPa. So it is almost vertically increasing. This is also very unusual. And so here, so I want to show you the field-induced superconductivity when the pressure is applying. Pressure is just above PC. So this is the magneto resistance at 1.45 GPa, just above PC. So at zero field, so we cannot get the superconductivity, but so under magnetic field, so there is a clear superconducting transition. This phase, from this results, sorry. So here, this is more clearly. So the field-induced superconductivity is clearly observed. So at 1 Kelvin, for example, or 2 Kelvin. And from this, so we construct the phase diagram. So the magnetic order or weak magnetic order phase is suppressed. And when the magnetic order phase is suppressed, superconductivity appears. So the evolution of HC2 curve, so above critical pressure is following. So just below PC, so it is HC2 curve is almost vertical, but applying the pressure, so superconductivity appears when the magnetic order is suppressed. And then, so further increasing the pressure, superconducting phase is pushed away to the higher field and lower temperature region, and finally disappears. And this reentrant superconductivity is resembled to the reentrant superconductivity above HM when the field is applying along 30 degrees from B to C axis. So here is the summary for ABC axis near the critical pressure. So magnetic ordered phase is here, and these are suppressing this field, and weak magnetic order is appearing something like this. From this, so we can speculate that this magnetic order is most likely antiferromagnetic order, not ferromagnetic order. And weak magnetic order is not long-range magnetic order. And to study the magnetic order under pressure, so we measure the magnetic susceptibility using the precious piston cylinder cell. So here is our small piston cylinder cell, copper beryllium piston cylinder cell. And so we measured up to 1.7 GPa above the critical pressure. And here is the evolution of magnetic susceptibility, ABC axis. So you can see here the ABC axis is quite anisotropic, so at ambient pressure, but increasing the pressure, so anisotropy is getting smaller and smaller, especially so the A-axis susceptibility along A-axis is decreasing rapidly. And A and B, the anisotropy between A and B axis is getting smaller and smaller. And finally, above the critical pressure, at low temperature, so anisotropy is exchanged. And so this, so if you look the inverse susceptibility, so surprisingly, so all the at all pressure, so the magnetic susceptibility shows a nice Curie-Weiss behavior. So you can see for A, B, C axis, and so the slope. So here you can see the slope of inverse susceptibility changing. So it means that the effective moment in changing as a function of pressure also. And so for the anisotropy, so above PC, so this is magnetization at zero at ambient pressure, but above the critical pressure, 1.7 GPa. So the anisotropy is drastically changing. The A-axis is rapidly decreased, something like this. And so from this, so we can say that it's not ferromagnetic. There is no ferromagnetic order. And here is a temperature dependence of magnetic susceptibility or ABC axis. So we can see that the anomaly TWMO and TMO. And so that these we can see the anomaly, but TWMO is just a crossover. And TMO, so we can see the clear kink, so at low temperature. This indicates most likely is antiferromagnetic order. And TWMO, we don't know yet what is the origin, but probably due to the short range order or some complex magnetic property and due to the multiple fluctuation, antiferromagnetism, ferromagnetism, valence, or Fermi surface instability. And finally, so I want to show you the evolution of T star or T chi max. So for A-axis, so we detect the T star anomaly, so 15 Kelvin. This is suppressing with pressure, and T chi max is also suppressing with pressure. And this is a temperature pressure dependence of T chi max and T star. So it is suppressing, and then so magnetic order appears. And what is interesting is T chi max or T star is immediately abruptly suppressed, disappears above PC. So it means the PC is probably the first order transition. And this T chi max is evolution of T chi max is scaled with metamagnetic transition HM, but at higher pressure. So it deviates from between the T chi max and HM. So this indicates that edging property is changing. So under pressure. And okay, so I think it's almost time. So I want to summarize my talk. So today I focus on the multiple superconducting phases under pressure detected in zero field. Zero pressure, zero field, and the multiple superconductivity also appears under magnetic field, revealing the very peculiar HC2 curve, and even we can see the reentrance field-induced superconductivity above the critical pressure, and above the critical pressure, antiferromagnetic order appears from the magnetic susceptibility measurement. Okay, so I stop my talk. So thank you for your attention.
Yeah, thank you very much. Yeah, this is a very interesting talk. Yeah, so you basically completely map out the phase diagram as a function of pressure as well as major susceptibility. So let me sort of take the advantage of asking you the first question. So basically, what you find is that as you gradually increase pressure, your stability along the A-axis is gradually reducing. So you know, from neutron scattering measurement, we know the spin fluctuations are basically ferromagnetic along A-axis, antiferromagnetic along B-axis, and C-axis is basically sort of two-dimensional. So does this actually tell you that from compared with the stability measurement? So does that compare? I mean, tell you that the ferromagnetism is actually bad for superconductivity in this system? Because your TC actually is increasing, right? With your TC is actually increasing, right?
Yeah. So of course, so you detected the antiferromagnetic fluctuation.
No, but it's
ferromagnetic.
It's antiferromagnetic along B-axis.
So ferromagnetic fluctuation
along A-axis is ferromagnetic. Along B-axis is antiferromagnetic. Yes. I'm sorry. Yeah, go ahead.
So so far I think the ferromagnetic fluctuation, there is no microscopic evidence so far.
Right.
But so myself, I believe there's also ferromagnetic fluctuation exists.
Oh, in the system. I see.
In the system. But so we don't know yet. So how it changing with pressure. So but so if you, well, I think it's from this evolution, the changing of anisotropy. So it seems so ferromagnetic fluctuation is reducing with with pressure, I guess. So this is my speculation, but there's no evidence clearly.
Yeah, but I mean, like I was saying, from neutron scattering measurement, we know the spin fluctuation along a-axis is sort of basically stays at gamma points. Basically, it's ferromagnetic fluctuation along a-axis, and the B is antiferromagnetic. So based on this phase diagram, I would argue that your ferromagnetism, because your susceptibility goes up, right, with decreasing temperature along A. So I would basically argue that the ferromagnetism is bad for superconductivity, at least naively, my naive thinking. Maybe JP, do you have any comments on this?
No.
I mean, this is just my pure speculation based on looking at this sort of a phase diagram, right?
I think it's more subtle, and the only point I would make is that we can't forget this is a correlated F electron system. So what about interband transitions and so on? We have to take all these things into account. I don't think we can interpret any of this so easily, but that's just a speculation.
Okay.
So, well, I want to show you some figure for the. I think here is the ferromagnetic interaction between this. And here, right? So for b-axis, so this is experimentally detected, and this is okay. But this c-axis ferromagnetic fluctuation is so far not detected experimentally.
No, but for c-axis, I mean, we basically, I guess the French group also confirmed, right? But we basically found that there's only sort of basically one peak situated at q = 0. So as far as we're concerned, it's basically two-dimensional. I mean, I agree. I mean, it's sort of ferromagnetic, but it's basically situated at q = gamma. I mean, but it's just, so it would be very similar. It seems to me it's very similar to the cuprids and nictite. Basically, most spin fluctuations are sort of basically two-dimensional, and it's and it's continuous along a-axis. So the a-axis is sort of the I would argue is the ferromagnetic axis, and b-axis is the antiferromagnetic axis, and c-axis is sort of I mean, basically a q = 0, or also basically you can say sort of irrelevant. I mean, I don't know. Yeah. Okay. Yeah. Sorry for taking up the first question.
Yeah, that's good.
Yeah. Are there any other questions?
I have a question. Yeah. Okay. So, very nice talk.
Thank you.
So regarding the TC versus gamma.
TC versus gamma.
Yeah. So you were talking about quality of sample being higher or lower. Do you have? I mean, are you only referring to the TC value, or are you talking about some other measurement of quality?
So this is so of course, so the best is to measure the residual resistivity to show the basically I think the TC should follow the Abrikosov-Volkov pair breaking theory. So, but well, experimentally, it's not so easy to evaluate the residual resistivity because it also depending on the current direction, and also there is some inhomogeneity in the sample. So one day, so we should measure. So we should clarify. So this point.
Okay, I was just curious because I wonder if you have any other data like X-ray or anything else that indicates.
The X-ray is always good, but so we by NMR experiment, so we measure the NMR spectra between the superconducting sample and the non-superconducting sample. And non-superconducting sample, the NMR spectrum is quite broad compared to the superconducting sample. So the superconducting sample is a very good crystal. So this is for sure.
This is interesting. Okay, thank you.
Yeah. So I have another question. I mean, so I guess you argued that there's a considerable density of states, right, from heat capacity point of view, and you argued as you increase TC or improve the quality of RR, of your sample, your densive states at the lower temperatures seem to get suppressed. So I guess my question is, I mean, so even for the best sample, there's still quite a bit densive states, right? So what is the reason for that?
This is the question, I think, is it's of course. So maybe, so let me show you the case for ferromagnetic superconductivity.
Yes.
So this is known. So the residual density of state is depending on the ordered moment. And this view is somehow easy to understand because I can show you, I want to show you some slide. So this is, so initially, so uranium ditelluride, so called half gap superconductivity. So this means, so the kind of A1 state. So in this case, one of the spin is gapped and the other is not gapped. Then, so there is a residual density of the state. But so this is the reason. But uranium ditelluride, there is no long-range magnetic order. So this kind of state cannot be simply believed. So then we think the residual density of state should be 0, basically. But this is a.
I mean, this is also, I mean, JP, you can confirm, right? This is also confirmed by STM, right? STM don't see still considerable densive states even at 0 energy, right?
Well, the comment I would make is that in all the thermal conductivity we've measured, there's no residual conductivity. So I don't call it density of states. I mean, unless it's extremely strongly scattered such that it doesn't conduct heat. So I don't know what it is. To me, it's some localized entropy. It's not an electronic density of states.
But I mean, I would have thought localized entropy would not contribute to heat capacity, right? Anything contribute to heat capacity should be, thermally excitable, right?
Well, I mean, look at, I can show you half-Weisler heat capacity that goes up to 10 joules per mole Kelvin. I mean, it's just magnetic entropy.
I see.
It's still a mystery. I agree.
So from your thermal conductivity measurement, you basically don't see quasi-particle that contribute to heat capacity, I mean, to thermal conductivity, right?
That's right.
I see. Yeah. Okay. I mean, are there any other questions by the audience? Okay, so there's a question from, does low quality samples show similar performance compared to high quality samples?
Similar
performance in terms of what? You mean in terms of upper critical field? Is there a drop in upper critical field for similar?
Basically, I think it doesn't. So of course, it's slightly different depending on the TC, but I think it's sorry. For example, this. So in fact, the TC here is a bit lower than the usual, 1.4 Kelvin. And nowadays, so we have 1.7 or 1.8 Kelvin. But between these, so the basically HC2 curve is quite similar. So there's no big change. So between this range, of course, the TC is very low. So of course, the HC2 is smaller.
Okay. So Zhichuan, you have a question?
Hi, nice talk. I have a question concerning so far, is there any evidence for pair density wave in this material?
Pair density wave?
Yeah.
I don't think it's so far, there's no such experimental evidence for the pair density wave. Why do you think so?
Yeah, because I mean, from the STM data, from the stat edge measurements by the URUC group, it seems that when they try to probe the local density of state, for the Majorana surface state, it seems that the particle hole symmetry is broken. So one possibility is that that there is pair density wave existing in this compound. So I'm just like wondering, is there any evidence so far?
But he said there's no evidence, right? Not as far as he knows.
Yeah, sure. Yeah, of course. Yeah, thank you.
Yeah. So I have another question. I mean, I was very curious about your statement about the NMR measurement showing a very small drop and suggesting that's evident. I mean, there are two questions actually. I was talking to NMR expert, Bill Hoffman. He was saying the problem with NMR is that it's very difficult to know whether NMR is really measuring the bulk or only the very the surface. That's one problem with NMR. And the other problem is that do people actually do you guys understand what is the reason for this small drop even though it's very small?
I think it's this drop is first. So this drop is depending on the magnetic field, of course, and so the depending on the d vector. So the d vector is with increasing the field, d vector can rotate. So then the drop of night shift is getting smaller and smaller with field.
I see.
So the Kenji Shidash has so he shows the field dependence of night shift, and night shift for b-axis is becomes almost zero at around 12 Tesla. Right. I remember. So but even at very low field, at close to zero Tesla, so night shift is quite small. The drop of night shift is quite small.
So do you have any comments on the criticism that NMR only sees the surface?
I don't think basically the night shift detects the detecting the good part of the sample, I guess. So I think it's not so.
It's not.
Of course, there's a skin. Yeah, I think it's not so sensitive. Yeah.
I mean, in the UTe2 argument. Okay, I understand your Okay. Okay. Yeah, that's very, very nice talk. Yeah. Okay. Are there any other questions? Okay. Yeah. If not, thank you so much. I mean, for staying up, get up so early for giving this talk. Yeah. We appreciate this very, very much. Yeah. Thank you.
Okay. Thank you very much.
Yeah. Thank you so much.
Okay. So